My name is Sankirtana and I'm from CSA F section, and my topic is CSA Design Pattern Analyzer for CPU GPU Architectures. Introduction to CSA Design Pattern Analyzer. The CSA Pattern Analyzer is a tool used to evaluate and optimize CPU and GPU architectures. The CSA Communication System Architecture. A design pattern analyzer is a tool used to analyze and optimize the design of communication systems, including communication systems. Some of the key features are design pattern analysis. Analyzes the design patterns used in the communication system, including error correcting codes, modulation schemes, and channel coding. Performance evaluation evaluates the performance of the communication system, including metrics such as bit error rate, packet error rate, and throughput. Optimization provides recommendations for optimizing the design of the communication system, including suggestions for improving error correction, modulation, and channel coding. Applications. The CSA Design Pattern Analyzer is used to analyze and optimize the design of space communication systems, including satellite communication systems and deep space communication systems. The CSA Design Pattern Analyzer is used to analyze and optimize the design of wireless communication system, including cellular network and Wi-Fi network. Benefits. The CSA Design Pattern Analyzer helps to improve the performance of communication systems, including reducing errors and increasing throughput. The CSA Design Pattern Analyzer helps to reduce the development time of communication systems by providing recommendations for optimization and reducing the need for trial and error testing. This analyzer facilities improve performance and efficiency in modern computing systems. Importance of architecture pattern analysis. Analyzing architecture pattern ensures optimal resource utilization. Architecture pattern analysis is crucial in designing and optimizing communication systems, including space communication systems. Benefits. Analyzing architecture patterns helps in identifying bottlenecks and optimization system performance. Pattern analysis ensures system reliability, reducing errors and downtime. Breaking down complex systems into patterns simplifies design and maintenance. Identifying patterns help reduce development and maintenance costs. Pattern analysis ensures reliable communication in space missions. Pattern analysis optimizes wireless network performance and reliability. Pattern analysis improves data center and cloud infrastructure efficiency. Key aspects. Breaking down systems into manageable components, designing systems to scale with growing demands, flexibility, adapting to change requirements and technologies. By analyzing architecture patterns, designers can create efficient, scalable, and reliable communication systems. The insights gained guide the design of the next generation CPU and GPU systems. Key objectives of CSA Pattern Analyzer: to identify prevalent design patterns in CPU and GPU architectures. The CSA Communication System Architecture Pattern Analyzer is designed to achieve the following key objectives. Identifying patterns. Identifying recurring patterns in communication system architecture. Analyze patterns to understand systems, behavior, and performance. Optimize system performance. Optimize system performance by identifying bottlenecks and area of improvement. Provide recommendations for improving system efficiency and reliability. Improve reliability. Identify potential failure points and vulnerabilities. Provide recommendations for improving system reliability and fault tolerance. Break down complex systems into manageable components. Simplify system designs and maintenance. Provide insights and recommendations to support design decisions, enable informed trade-offs between completing design goal, identify reusable patterns and components, enable reuse of proven designs and components. By achieving these objectives, the CSA pattern analyzer helps designers and architects to create efficient, scalable, and reliable communication systems. To provide recommendations for architecture improvement based on pattern analysis. Core components of the CSA analysis tool. Pattern recognition engine that detects common design motifs. This, the CSA analysis tool consists of the following core components. Pattern recognition engine identifies recurring patterns in communication system architecture, analyzes patterns to understand systems behavior and performance. System modeling creates a model of communication system architecture, represents system components, interface, and relationships. Performance analysis analyzes system performance, including metrics such as bit error rate, packet error rate, throughput, and latency. Identifies bottleneck as and areas of improvement. Optimization engine provides recommendations for optimizing system performance, such as improvements to system architecture, component selection, and configuration. Visualization provides a graphical representations of system architecture and performance, enables user to visualize and understand complex system behavior. Reporting generates reports on system analysis and optimization results, provides recommendations for future improvements and upgrades. These core components work together to enable the CSA analysis tool to analyze and optimize communication systems architecture, improving performance and reliability and efficiency. Common CPU design patterns. Common CPU design patterns. CPU design patterns are reusable solutions to common problems in CPU design. Here are some common CPU design patterns. Pipelining breakdowns instruction execution into stages, increases instruction throughput, and reduces latency. Branch prediction. Branch prediction predicts uh, brands. Cache hierarchy uses multiple levels of cache to reduce memory access latency, improves performance by reducing memory access time. These CPU design patterns are used to improve performance, reduce power consumption, and increase efficiency in modern CPUs. Common GPU design patterns. Massive parallelism through thousands of cores. Use of SIMD execution model, memory hierarchy optimized for high bandwidth and low latency. Pattern detection techniques in CSA analyzer. Static analysis of hardware description code. Pattern detection techniques in CSA analyzer. The CSA analyzer uses various patterns detection techniques to identify recurring patterns in communication system architectures. Graph-based pattern matching, machine learning-based pattern matching, rule-based pattern detection, statistical pattern analysis, structural pattern analysis, behavioral pattern analysis. These pattern detection techniques enables the CSA analyzer to identify recurring patterns in communication system architectures, improving system performance, reliability, and efficiency. Impact of design patterns or performance. Certain patterns can lead to increased out throughput but may cause bottlenecks. Design patterns can significantly impact the performance of system. Here are some ways to design patterns can affect performance. Positive impacts: improved modularity, reusability, easier maintenance. Negative impacts: over engineering, performance overhead, increased complexity. By understanding the impact of design patterns on performance, developers can create efficient, scalable, and maintain systems. Case study: Superscalar CPU pattern. The pattern involves multiple instructions issued simultaneously. CSA analysis reveals pipeline hazards and resources conflicts. Results guide modifications to improve instruction scheduling. CPU GPU memory hierarchy pattern. High bandwidth memory access is critical for GPU performance. Analysis identifies bottlenecks caused by memory contention. Recommendation includes optimization memory access patterns for better throughput. Benefits of using CSA pattern analyzer enables early detection of architectural inefficiencies, support informed decision making due to hardware design. Challenges in pattern analysis for CPU and GPU. Complexity due to vast number of possible designs patterns. Variability in workload behavior complicates analysis. Need for high fidelity simultaneous simulation tools and accurately model performance. Integration with design workflow. CSA analysis can be embedded into hardware development pipelines. It complements other design verification and validation tools. Future trends in pattern analysis. Enhanced machine learning models for more accurate pattern recognition. Real-time analysis capabilities during hardware simulation. Practical applications of CSA design pattern analyzer. Performance tuning for high performance computing systems. Benchmarking and comparative analysis of architecture variants. Limitations and considerations. Accuracy depends on the quality of input models and data. Complex patterns may require extensive computational resource to analyze. Continuous updates are necessary to keep a pace with evolving hardware designs. Key takeaways. CSA design pattern analyzer is vital for understanding and optimizing CPU and GPU architectures. Recognizing and analyzing data patterns leads to performance improvements. Integrating pattern analysis into development processes accelerates hardware innovation. Con- Conclusion. The CSA pattern analyzer is a powerful tool for modern hardware design. It bridges the gap between theoretical architecture patterns and practical performance. The CSA pattern analyzer is a powerful tool for the modern hardware design, enabling designers to identify and optimize patterns in communication system architectures, improving reliability and efficiency. The CSA pattern analyzer is a key enabler for modern hardware design, allowing the designers to create complex systems that meet the demands of emerging technologies. Ongoing advancements will further enhance its capabilities and applications. These are the references. Thank you.